Welcome to Online Linear Algebra, and in this video we will be discussing vectors and matrices and how matrices are storage spaces for vectors. The physics definition of a vector is that it is a directed line segment with magnitude and direction. That means it's a segment in which you have a starting point called the initial point and an ending point called the terminal point. If vectors are equivalent, it means that they have the same magnitude and direction. It doesn't necessarily mean that they have the same starting and ending point, but if you did pick one vector up that was equivalent to another vector and you set it at the initial point of this other vector, it would end at the terminal point of the other vector. So they have the same magnitude and direction. The image here shows the blue and the red vector as equivalent vectors. If vectors are opposite, it means that they point 180 degrees from each other. That is that they are scalar multiples of -1. So 1 multiplied by the scalar -1 gives you the other one. The green and the blue vector in the video here are opposite vectors. Notice the terminal point when you start at 0, 0, 0 is -2, 3, 1 for the blue vector, and it is +2, -3, -1 for the green vector. That's an example of opposite vectors. In linear algebra, we usually picture our vectors starting at the origin. And so the terminal point is really the important point for us in linear algebra. In fact, sometimes vectors can just be represented by their terminal point, and we treat vectors somewhat like they just are points in space. If you watch the video from the Essence of Linear Algebra, he talks a little bit more about that. In vector land, scalars are real numbers, or maybe I should say real numbers are called scalars. It's called a scalar because the job of a scalar is to multiply vectors, and when you multiply a vector by a scalar, you scale the vector. The vector either becomes longer than it was or shorter than it was, meaning you might scale the vector to be 5 times the length it was, or you might scale the vector to be only 10% of the length it was. Shown here is an example of taking the scalar 3 and multiplying the vector -2, 3, 1 by the scalar 3. Notice the arithmetic is what you would think it would be. I multiply each component by the scalar, and in this case I would get -6, 9, 3 as my scalar multiple of -2, 3, 1. That vector is shown as a green vector, which is longer than -2, 3, 1. It's actually 3 times as long as -2, 3, 1. I also could scale by negative numbers. So here's an example in which I'm scaling -2, 3, 1 by this number -1.5, again by the scalar -1.5. And again, the arithmetic is what you would think it would be. I take -1.5 times -2, I get +3. -1.5 times 3 gives me -4.5. -1.5 times 1 is -1.5. So notice that that scalar multiple creates a vector that's 180 degrees from the vector that you are multiplying. It's shown in the image as a purple vector. So 3, -4.5, -1.5 is 180 degrees in direction from -2, 3, 1. But it's also scaled 1.5 times longer than -2, 3, 1. So you could see it is a little bit longer than -2, 3, 1. The magnitude of a vector just means the length of it. And if you were in 2 or 3 dimensions, you might want to just picture a right triangle, because that's really what you are doing. You're finding the length of the hypotenuse of a right triangle. On this image, we have some examples. One is the vector starting at the initial point 0, 0 and going to 10, 5. You can see the right triangle formed. The length in the x direction, 10, forms one side of the right triangle. The length in the y direction forms the leg of the other right triangle. So the magnitude or length of my vector is the length of the hypotenuse. And so Pythagorean theorem comes into play here. So I take the x direction, 10, I square it, I get 100. I add the y direction squared, I get 25. So 100 plus 25 is 125. So the length of the vector is the square root of 125. Again, just a straightforward application of Pythagorean theorem. Another example is showing a vector starting at the origin, going to -8, -3. Just because the directions are negative does not make the lengths change. I'm still moving 8 spaces in the x direction. I'm still moving 3 spaces in the y direction. So if I square -8 or I square 8, I get 64. If I square -3 or I square 3, I get 9. 64 plus 9 is 73. So the magnitude of that vector is the square root of 73. And if you extend this to 3 dimensions, you are just going to square each component. You're going to square x, you're going to square y, you're going to square z, and add them. Take the square root. That will give you the magnitude of a vector in 3 dimensions. If you're in 4 dimensions, I know we can't draw a picture of it, but the concepts stay the same. I would square x and y and z and whatever you want to call the 4th dimension and add those results and take the square root, and that would give you the length of the vector in 4 dimensions. Doing so is still using Pythagorean theorem. You're just first, for 3 dimensions, you draw a right triangle for 2 of the components, get that length, and then that forms the side of a second right triangle. So you do Pythagorean theorem twice for 3 dimensions, you do Pythagorean theorem 3 times for 4 dimensions, etc. But it's probably just easier to kind of picture Pythagorean theorem and just realize the same concept extends into higher dimensions. If you assume that your vectors start at the origin and you then list the terminal point by its x component and its y component, it's also true if you're in other dimensions. So if you list the x, the y, the z in 3 dimensions, you're listing the component form of the vector. So assuming your vector starts at the origin, if you list the coordinates of the terminal point, you are stating the component form of a vector. Notice when you're in 2 dimensions, there is this nice relationship between x and y and the magnitude and the angle that the vector forms with the positive x-axis. So again, just using right triangle trigonometry. So cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. You can figure out that the x component is always given by the magnitude of the vector times cosine of the angle formed with the positive x-axis. And the y component is always the magnitude times the sine of the angle formed with the positive x-axis. When I say the angle formed with the positive x-axis, I also mean that we're measuring counterclockwise. So we're going through quadrant 1, then quadrant 2, then quadrant 3, then quadrant 4. So if you always measure your angle from the positive x-axis in that direction, then if you're in 2 dimensions, the x component will always be the magnitude of the vector times cosine. Y will always be the magnitude of the vector times sine. If we add vectors, what we're doing is we're literally picking one vector up and stacking it at the end of the other vector without changing the direction of either vector. So here I have -8, -3 being added to 10, 5. So the green vector is the -8, -3, and the blue vector is the 10, 5. So I'm stacking 10, 5 at the end point, the terminal point of -8, -3. Notice when I do that and I don't change the direction of either vector, I land at the point 2, 2. So adding those two vectors together is equivalent to starting at the origin and going to the point 2, 2. Notice if I take -8, the x of the one vector, and I add it to 10, the x of the other vector, I get +2. If I take -3, the y of the one vector, and I add it to 5, the y of the other vector, I also get 2. So when you add vectors, you literally just are adding the x's, adding the y's. If you're in 3 dimensions or 4 dimensions or 5 dimensions, you're going to just keep that same pattern up. You're going to add the z's together. You're going to add the w's together, or whatever you're calling your fourth dimension, etc. So you add like components, and that gives you your sum. But if you are geometrically thinking about what you're doing, you literally are taking one vector, stacking it at the end of the other vector, not changing the direction of either one, and that is the result of adding the vectors. It is also nice to note that the order that you add vectors doesn't matter. If I stack one vector to the end of the other, I'm going to land at the same point as if I did the reverse. You can see that in the picture here. If I take -8, -3, and I stack it at the end of 10, 5, I'm still going to land at the point 2, 2. When you subtract vectors, you're still stacking a vector at the terminal point of another, but you reverse the direction of the vector you are subtracting. So for example, if I took 10, 5 and I subtracted 8, 3, okay, so I'm subtracting 8, 3, it's equivalent to adding -8, -3, and I still land at 2, 2. So 10, 5 added to -8, -3 is the same as 10, 5 subtracting +8, +3. So you're still stacking vectors at the terminal point. If you're subtracting, it means you've reversed the direction of the one you were subtracting by 180 degrees. And the arithmetic is what you would think it would be. 10 minus 8 is 2, 5 minus 3 is 2. In linear algebra, there are 3 types of products with vectors. We've already talked about the scalar product, multiplying a vector by a scalar or a real number. In terms of multiplying vectors, you could find a dot product and you can find a cross product. We actually really won't be focusing on a cross product. We will bring it up in chapter 6 when we're talking about vectors in that chapter. The cross product can be used to find the equation of a plane between vectors in the plane. If you've taken Calc 3, you should be already familiar with that. If you have not taken Calc 3, don't worry about it. But we will be focusing on dot product. So the dot product is the sum of the product of like components. So if I'm dotting two vectors, I multiply the x components together, I multiply the y components together, and I add them. So a times c plus b times d is the dot product of these 2 by 2, these vectors that are in R2. If I was in 3 dimensions, I do the same thing, but I'm going to add the product of the z's. If I was in 4th dimensions, I would do the same thing, but I would add the product of the z's and the 4th dimension, etc. So if I took -2, 3, 1, 5, 6, 2, both of those vectors are in R3 or 3rd dimension. -2 times 5 is the product of the x's, it's -10. 3 times 6 is 18. 1 times 2 is 2. So I then add the product of the x's, I add the product of the y's, I add the product of the z's. -10 plus 18 plus 2 ends up being 10. So the dot product of those two vectors is 10. Notice the dot product is a number. The dot product is not a vector. You get a scalar number as your dot product. If I have the vectors -2, 8, and I dot it with 4, 1, notice that -2 times 4 is -8, and 8 times 1 is +8. And -8 plus 8 is 0. So in this case, my dot product ended up being the scalar 0. That happens when vectors are perpendicular. So if you see that the dot product between two vectors is 0, it means that those vectors are perpendicular. Again, that idea extends into 3 dimensions and 4 dimensions and 5 dimensions, etc. If the dot product is 0, it means those vectors are orthogonal or perpendicular. Orthogonal is another word that means perpendicular. I've been mentioning 3 dimensions and 4 dimensions and 5 dimensions, so just a reminder, vectors can be any length or dimension. So here are some examples. The vector 3, 6, 7, -1, 0. That's an example of a vector in R5 or in the 5th dimension. I can't draw a picture of dimensions higher than 3, but a lot of the concepts that we're going over just extend right into other dimensions. Like the processes that we do, you do the same thing just in higher dimensions. For example, we talked about finding the dot product. The dot product is the same process whether I'm in 2 dimensions or 3 dimensions or 4 dimensions. I multiply like components. I multiply x's by x's, I multiply y by y, I multiply z by z, etc., and then I add those products. We talked about the magnitude of a vector. How do you find the magnitude of the vector? It's the square root of the x component squared added to the y component squared. If you're in 3 dimensions, you then add the next component squared. If you were in 4 dimensions, you would add the next component squared. So just a reminder that a lot of the mechanics do not change just because we're moving into other dimensions. And because we live in a 3-dimensional world, we can't really draw pictures higher than 3 dimensions, but you can kind of make analogies by picturing 3 dimensions or 2 dimensions. The vector -2/3, 6.25, 1, 8.10, 12.73, 4/5, 100 is in R8. Notice I purposely was pointing out that the components of a vector can be any kinds of numbers. So you can have fractions, you can have decimals, you can have 0. You're not limited to just integers as your components. Why would we want vectors in higher dimensions? Well, projects can contain a lot of variables. For example, you might have a product that has a width and a length and a height and an area of a base and a volume and a weight and a price. All of those variables might be something you're studying. And so if you list them all, you've created a 7th dimensional vector. That would be an application of a 7th dimensional vector. All spaces, whether you're in R2 or R3 or R4, has a 0 vector, which means all the components are 0, and the 0 vector has dimension 0. So a single point, has dimension 0, whether the rest of what you're dealing with is in any other dimension. Okay, so 0, 0, 0 has dimension 0. A single point has dimension 0. If you're in R1, so the first dimension, you just have a single number. So 5 is an example of a vector in R1. I just have a single number. And that would be a vector that points in a direction length 5. So you can kind of just picture like the X number line, just picture a number line, and 5 would mean you've moved 5 spaces on that number line. Okay, so what are matrices? Matrices are storage for vectors. I have an example of a matrix which has size 4 by 6 on this slide. Okay, so when we're listing the size of a matrix, you list how many rows you have first, and then you list how many columns you have. So this matrix is 4 by 6. So I can view it as columns of 6 vectors in the fourth dimension, or in R4. I can also view it as 4 rows of vectors in R6. So I have 4 rows and the vectors have 6 components, hence they're vectors in the 6th dimension. R6 is another way to represent the 6th dimension. Or I could see it as 6 columns where the vectors are all in the 4th dimension. And when you're listing the vectors like this in a matrix, you assume that the initial point is the origin. I mentioned that earlier, that in linear algebra, our vectors are generally going to be considered with initial point at the origin, 0, 0, 0, or 0, 0, 0, 0, whatever dimension you're in. And the components then are telling you where the terminal point is. So 1, 2, 0, 2 is the terminal point of a vector in R4 that starts at the origin. 1, 3, negative 2, 0, 2, 0 are the components of a vector that starts the origin in the 6th dimension and lands at the terminal point given by 1, 3, negative 2, 0, 2, 0. Here is an example of a 10 by 8 matrix with an application involved. I could look at this as 10 rows in which each row is telling me a different cookie order of the 8 different kinds of Girl Scout cookies, or I could look at it as 8 columns in which each column is telling me how many of that type of cookie got ordered by 10 different customers. So once again, it could be viewed as 8 rows of vectors that are in R8, the 8th dimension, or I could look at it as 8 vectors in the 10th dimension. When you add matrices, you add like components, and so the matrices have to be the exact same size. You add the first row, first column to the first row, first column. You add the second row, first column to the second row, first column, etc. So matrices have to be the exact same size if you're going to add them. Here's an example. I have 2 3 by 3 matrices. I have 3 rows and 3 columns. The first row is representing the sandwiches of food truck friends for truck 1 and truck 2. Row 2 is representing ice cream, and row 3 is representing beverages. So if I add these two together, I get the total number of hamburgers sold overall. I get the total number of chocolate ice cream sold overall. I get the total number of buy drinks sold overall, etc. So if you think about how in math in general, you always add like terms, in algebra class, x's can get added to x's and y's can get added to y's. The square root of 2 can get added to another square root of 2, but you can't add the square root of 2 to a square root of 3. You can kind of think of this as that same idea. I can add like terms to like terms. So if I'm adding matrices, I have to have the exact same size. Now, sometimes in an application, you might have matrices that are not the exact same size, but you force them to be the exact same size by adding some rows or columns of zeros. Sometimes you can go ahead and do that. Sometimes if you do that, it actually, creates some kind of meaning problem in which, the meaning gets messed up. But, for the most part, that's usually an option if you really do want to add matrices and they are not the exact same size. But in general, the rule is if you add matrices, they need to be the exact same size. Here we're finishing our application about the food truck friends, and We have some numbers here for number of hamburgers, brats, and veggie patties, and chocolate, vanilla, and pistachio ice cream, and buy drinks, and Snapple drinks, and peak tea. And if I add the two matrices, I see that a total of 520 hamburgers were sold, 593 brats were sold, 308 veggie patties were sold, 396 chocolate ice cream, 470 vanilla ice cream, 414 Snapples were sold, etc. So that kind of emphasizes that you're adding like things to like things. I'm adding hamburgers to hamburgers. I'm adding chocolate ice cream to chocolate ice cream. I'm adding Snapple to Snapple. You're not adding the brats to the pistachio ice cream, for example. We mentioned dot products earlier because when you multiply matrices together, you are forming dot products. You are dotting a row from the first matrix with a column in the second matrix. So for example, my first matrix has 3 rows. So I've identified that matrix as vector 1, vector 2, and vector 3. I'm reading those vectors across. Negative 2, 5, 6, 10 is the top row vector of that first matrix. The second matrix, I'm looking at it as 2 column vectors. So negative 5, 3, 14, 6 is an example vector in that second matrix. So when you multiply matrices, first you make a decision on what order you're multiplying them. And when you make that decision, the first matrix, as you read left to right in the product, you read those rows as vectors, and the second matrix in the product, you read the columns as vectors. And you're dotting row 1 with column 1, row 2 with column 1, row 3 with column 1. And that creates your first column in the product. And then you dot row 1 with column 2, row 2 with column 3, row 3 with column 3, and that creates your second column in the product. So notice the number of rows of the second vector has to match the number of columns of the first vector. So my first vector is 3 by 4. The second matrix has to be 4 by something. In this case, it's 4 by 2. My product then ends up being a 3 by 2. It has the same number of rows as the first and the same number of columns as the second. So again, you're dotting rows down columns. And so if you have an M by N, your second matrix that you multiply it by needs to be an N by something else. The columns of the first have to match the rows of the second. And then the size of the product will be M by P, where M is how many rows the first vector had, and P is the number of columns of the second vector. So my example here, I had a 3 by 4. I multiply it by a 4 by 2, I get a 3 by 2 as my result. So here we are computing those dot products. I'm showing all the arithmetic of computing those dot products, and notice then my product of that first matrix by that second matrix is a 3 by 2. I have the same number of rows as the first and the same number of columns as the second. It forms a 3 by 2. Examples of multiplying matrices is limited as your imagination. So the bigger your imagination, the more examples of multiplying matrices you're going to be able to come up with. Here's an example in which the Shangri-La Fine Art Museum is giving golden members free admittance, 10% discount at the gift shop and the restaurant, and a 50% discount on special event tickets. The platinum members are getting free admittance, 20% off in the gift shop and the restaurant, and a 75% discount to special events. Sherilyn Seashell looked over her receipts from the last 3 years of visiting the Shangri-La Fine Art Museum, and she determined that she spent the following amounts on admission, food, gifts, and attending special events. We're going to find the product and interpret the meaning. So notice if you have a gold membership, you get a 100% discount on admittance because it's free. You get a 10% discount in the gift shop and the restaurant. You get a 50% discount on the special events. If you have a platinum membership, you get a 100% discount on the admittance because it's free, 20% discount in the gift shop and the restaurant, 75% discount on the special events. And Sherilyn found that in year 1, she spent $120 to get into the museum, so $120 on admission. She spent $284 on the gift shop and the restaurant. She spent $150 on special events. Year 2, she went a little bit less. She spent $180, or actually, I guess she spent more on admission, but she spent less in the gift shop and the restaurant and less on the special events. Year 3, she spent $144 on admission, but $252 in the gift shop and the restaurant, and $200 on special events. So notice we are able to multiply these because the first matrix is a 2 by 3 and the second matrix is a 3 by 3. So the columns of the first match the rows of the second. So I'm able to go across the rows of the first and down the columns of the second. I can multiply them. So taking 100% times 120 and then adding 10% times 284 and then adding 50% times 150. So notice again, I'm making a dot product, so I'm multiplying. 100% is 1, so 1 times 120 plus 0.1 times 284 plus 0.5 times 150, and I get a result of $223.40. So that was going across row 1, down column 1. Now I'm going to go across row 1 and down column 2. So 1 times 180 plus 0.1 times 196 plus 0.5 times 75. And I get 237.1. Then I go across the row and down the column. I get 1 times 184 plus 0.1 times 252 plus 0.5 times 200, and I get 269.2. If I go across row 2 and down column 1, I'm doing 100% or 1 times 120 plus 0.2 times 284 plus 0.75 times 150, and I get 289.3. If I go across row 2 and down column 2, I'm doing 1 times 180 plus 0.2 times 196 plus 0.75 times 75, and I get 275.45. And then last but not least, I go across row 2, down column 3, 1 times 144 plus 0.2 times 252 plus 0.75 times 200. I get 344.40. So these give me the total saved in years 1, 2, and 3 if she had the gold membership or the platinum membership. So if she had the gold membership, she would have saved $223.40 if she had had the gold membership during year 1. If she had had the platinum membership during year 1, she would have saved $289.30. If she had had the gold membership in year 2, she would have saved $237.10. If she had had the platinum membership in year 2, she would have saved $275.45. And if she had had the gold membership in year 3, she would have saved $269.20. If she had had the platinum membership in year 3, she would have saved $344.40. So at this point, she would have to figure out what the membership cost and whether it was worthwhile for her to get the different kinds of memberships. Okay, so we've talked about scalar multiples of vectors. We've talked about adding vectors. We've talked about multiplying vectors and what a dot product is. We've now talked about multiplying matrices. Another operation involving matrices is the transpose. And the transpose is kind of what the name indicates. You transpose the rows and make them columns and vice versa. So if I took the 3 by 2 matrix that I have here called A, where I have 3 rows, 2 columns, its transpose now has 2 rows, 3 columns. So 6, 8, 10 was a column. 6, 8, 10 is now the first row in the transpose. 7, 9, 11 was the second column. 7, 9, 11 is now the second row of the transpose. Notice in example B here, I have a 3 by 3. And so if I make the transpose, the first row becomes the first column. So negative 1, 4, 3 is now the first column. 8, negative 2, 9 is now the second column. 5, 10, 4 is now the third column. Notice that the diagonal stays in place. Negative 1, negative 2, 4 is still on the diagonal, but the 8, 5, 10, which was in the lower left, is now in the upper right, and the 4, 3, 9, which was in the upper right, is now in the lower left. So when you have square matrices, the transpose literally is a reflection about that diagonal. This video was an introduction to vectors. All of the important basic vocabulary was covered. A vector is a directed line segment with an initial point and a terminal point. In linear algebra, we tend to have initial point the origin. So the terminal point is the components, the actual point that you land on as you move from the origin to the terminal point of your vector. So in linear algebra, the terminal point could actually kind of just represent the vector. The length is the square root of the sum of the components, and the scalar multiple is a real number times your vector, and it scales it to make it longer or shorter. If you multiply a vector by a negative, it flips it around 180 degrees. Matrices are storage spaces for vectors, and you can read the matrix as having column vectors or row vectors. And then we talked about how to add vectors and add matrices, and we talked about how to multiply matrices. So those were all the important concepts in this video. Again, I also recommend that you watch the Essence of Linear Algebra video about vectors. The gentleman in that video gives you some other perspectives that is very useful for linear algebra.